Okay, are you copying okay?
We got you.
Okay, good. Well, I had the pleasure of first meeting Philip Tate when I became a member of the Eccleford Amateur Radio Society in Ashford, Middlesex, England. Uh, Phil has an amazing background. He graduated with a BS, Bachelor of Science degree in Applied Physics and Chemistry in 1980 and quickly found employment with the Plessey Electronics Research Company. And for 4 years, he worked on the design and development of infrared pin diode detectors for optical fiber telecommunications, culminating in what was acknowledged as the world's fastest 1.6 microns detector, micrometers, infrared wavelength in 1983. In 1984, he changed tack and started working in the field of electron beam lithography for specialized electro-optical devices, including wafer-scale active waveguides and switches. In 1988, he returned to academia and spent 5 years as a salaried research fellow working on the development of electron beam lithographic resist, during which time he submitted his thesis and graduated with a PhD in 1992. I love this part. In early 1994, overage, overskilled, and overqualified, and thus unemployable, he became a tenured lecturer in physical chemistry at a London university and acquired his postgraduate teaching qualification. He continued research for many years into lithographic materials and high mechanical performance rigid polymer foams before tiring of fighting research bureaucracy and concentrating on teaching. He taught a variety of subjects, including electrochemistry, remedial math, analytical science, statistics and computation, and materials science at all levels from freshman to masters, plus mentoring a wide variety of PhD candidates. He passed his radio amateur's exam in 1981, but life got in the way and he did not take out his license and call sign Mike 1 Golf Whiskey Z until 2002, following an inspirational first trip to the Dayton Hamvention the previous year. In 2015, he discovered that he had accrued sufficient capital to retire. The following year, he joined the Eccleford Amateur Radio Society, and before he knew it, some fool had made him secretary of the club, a post that he still holds, probably until death. He is married to Caroline, and they have a grown son, Alex, who also has his PhD. However, he is a very rare species, a qualified philosopher in full employment. So, Philip, if you're ready to dance, Mike will switch you over to the sharing.
Philip,
Okay.
Philip, you've got control.
Thank you. Right. Okay. Let's call this up. Right. Can you see my opening slide?
Yes, we can.
You can. Okay. And is my voice clear enough for you?
Yes.
Thank you. I won't wait for everybody to answer. I only need one of you to answer. Then it's not my problem. Well, good evening, everybody, ladies and gentlemen, and thank you very much for inviting me to give a talk to you tonight. Before I kick off on the main, excuse me, subject of the talk, let me make it clear I'm not an expert on the TinySA spectrum analyzer. As a retired lecturer, I realized that all I have to do is to maintain a thin veneer of knowledge. above and beyond what most of you know. And there's a very good chance with the very, pleasing numbers of you that have turned out for the meeting tonight. There's a very good chance that some of you have a much thicker veneer of knowledge than I do. If I make a fool of myself, it's not too bad. But if in doing so, I embarrass Neil, who gave me that lovely introduction there, then that would be unforgivable. So I will do my best not to do so. Again, because of the numbers, and I don't know you and I don't know, but you obviously have a wide range of backgrounds there. I'm just going to briefly explain what a spectrum analyzer is before I start talking about this one. A spectrum analyzer is a device that separates frequencies in a complex oscillatory system. Shall we put it that way? It could be sound. I think I'm sure some of you have experience of audio spectrum analyzers, showing how different frequencies of sound in a voice or in music or so on may be distributed. It could be radio frequency, which is the subject tonight. It could be gamma rays, X-rays, neutrons, you name it. And generally, it presents a graph, usually of, what should we say, intensity, power, energy, amplitude, however you like to describe it, or indeed display it, against frequency, or for the benefit of those of you who know better and not wishing to look a complete fool yet, shall we say narrow bands of frequency. If you don't understand that last comment, don't worry too much about it. Now, spectrum analyzers have been around for a good few years now, decades even, and there are a number of different ways you can achieve this aim of displaying different frequencies and their relative amounts over a range. The old-fashioned way, of course, was the analog way, which I'm sure a lot of us remember. And the easiest way to do spectrum analysis in an analog system is to have a fairly narrow bandpass filter and to sweep it across the range of frequencies that you're interested in and measure the output from the filter at those different frequencies and display them. Now, this can be a very, very simple device. For example, I have one that is little more than a varactor or a varicap tuned crystal set, which does the job, and it's not accurately calibrated. Its only job was to look at the output of small transmitters and look for the presence of harmonics in the output. So it can be quite simple. The problem with that particular type of device is the time it takes to sweep the filter across the frequency range. Often that can be quite slow, and that means that what you get at the end of the day is not a snapshot. It's you know, by the time you get to the end of the pass for the display, what is presented at the beginning may be very different. A better way of doing it is to have multiple bandpass filters, one for every frequency that you're interested in, and run them in parallel and sample them all simultaneously and display the results. Obviously, that's can be rather expensive. You may need a lot of bandpass filters to get the resolution you want, and it's somewhat inflexible, because if you want to change frequency range, changing the frequencies of all those bandpass filters can be a difficult thing to do. So neither of those solutions is perfect by any means, but there are some very good analog spectrum analyzers out there. Moving into the digital realm, how we analyze signals in the digital realm is to sample them the entire frequency range over a period of time, and then to change from the time frame to a frequency representation within that. And a French mathematician by the name of Fourier showed how to do that over 200 years ago. If you have to do it by hand, it can be quite tricky, without a doubt. But we have computational ways now, of course, of being able to do this in the form of what's commonly called the fast Fourier transform. And this is a digital method of analyzing a signal acquisition with time to the frequency domain and displaying it. Nice thing about the fast Fourier transform is that it can be platform or processor independent. The principles of programming a fast Fourier transform have been known for, again, decades, and you want it faster, you want it accurate, more accurate, you want a better resolution, you just throw a bigger and better and faster processor at it and more memory. So it's kind of independent of the processor system you use, and effectively constantly upgradable. Of course, like everything else, there's a compromise. There has to be a downside, and the downside of the fast Fourier transform digital process is that it always, and I emphasize this, it always introduces artifacts or spurious signals, sometimes shortened to spurs, in the output. There's no way around it, unfortunately. You will always, there are ways of mitigating it, there are ways of reducing it, but you will always get some artifacts in the output that are not real. And I emphasize that now because a lot of what the TinySA and other spectrum analyzers, digital spectrum analyzers, is about is to do with reducing or noting and taking steps to reduce those artifacts. That's very, very important. Actually, the TinySA is very good in one respect, very clever in one respect, because it actually uses a combination of techniques. It's a hybrid device. It separates up the range of frequencies that you're looking at with separate bandpass filtered sections, analyzes each digitally, and then stitches them together on the display. So it kind of does its best to combine the best of both worlds. And I must say, to a budget, okay, to a size and to a budget. But otherwise it does pretty well. Oh, right. That's when my keyboard doesn't work. Okay. Right, what do you get for your 60 bucks when you buy a TinySA? Well, of course, it arrives in a lovely looking box of beautifully textured ebony with solid gold writing on the top. Okay, the ebony actually feels more like cardboard, and the gold printing does not conduct electricity. So I have my suspicions about it. But okay, it comes in a nice box. That's the important thing. Inside the box, this is what you get. You get the tiny spectrum analyzer, the TinySA itself. You get two male-to-male SMA leads that are actually quite nicely made. One female-to-female SMA adapter, which can come in useful. You get a short telescopic antenna, of which I will describe more later. A USB type 2, that's what us old people call a proper USB connector, to a modern USB-C type connector. And this can be used both for charging the device with its internal battery and also as an interface cable to connect it to a computer if you want a better display or more processing options and so on and so forth. I have to say it lasts many hours on one charge. I charged mine up when it arrived several weeks ago. I played with it intermittently. It's not even close to the battery going down. I believe it claims at least 8 hours continuous operation. I can believe that, probably exceeds that actually. You also get a short lanyard with a touch screen device on it that looks a bit like a guitar pick with a hole drilled in it. This is because it's a guitar pick with a hole drilled in it. It's there and useful. Personally, I don't use it much myself. I prefer to have a proper a touchscreen stylus and use that, and I keep one handy for that purpose. It does not come with a manual. It comes with a little sticker that you can't quite see in the box there that's labeled http://tinysa.org. But that does not mean that it does not have good supporting information available on the internet. It does, and I'll say more about that in just a minute. Sorry, it does annoy me that my keyboard doesn't work in these circumstances. I have to use that. Does it remind you of anything? Well, if you own a Nano VNA from a couple of years ago, it probably does. It has a similar look and feel, and that extends also to the software that, or the firmware that runs on it, I should say. The frequency selection and so on and so forth is done with the same menu structures as are used on the Nano VNA. So it's designed specifically to have this kind of matching form factor. Okay, it's a 2.8-inch screen. That, of course, is the diagonal size, as the early Nano VNAs were. You can still get them with that screen size. There are now Nano VNAs, of course, with 4-inch screens. In case you're waiting for the 4-inch screen version of the TinySA to come out, don't hold your breath. There are currently no plans for a 4-inch version. I'm sure they'll come. I'm sure they will be available, but it's not high on the priorities list. Now, having said that, they look very similar. You can see the sockets are arranged similarly. They've got the same on-off switch, the jog connector, control at the top, and so on and so forth. Sockets are located in much the same way. The similarity between these two devices ends there, right? They are not designed by the same people at all. The Nano VNA was designed by a Japanese amateur who put everything on the World Wide Web for other people to contribute to. I forget what his actual name is, because he always goes by the moniker EDY888, I think, in everything he did. As a result of this, because of an unfortunate circumstance that arose unintentionally, he didn't protect this in the Nano VNA as an invention, and he immediately got the Chinese factories stepped in and said, right, it's unprotected, anyone can make it. And as some of you may know, some pretty awful versions of the Nano VNA actually did come on the market. They are now covered by a company called Hugen, I think it is, that now at least takes some steps to ensure proper construction and so on, and distribution of the true Nano VNA. The TinySA, on the other hand, was designed and developed by a Danish engineer by the name of Erik Kushøk. And it's a completely independent design. All he did was to get permission to make it, to use the same form factor and, as far as possible, the same kind of components that were used in the Nano VNA, obviously because of its popularity. The device that he came up with, I personally think is very well engineered. It's in two sections. You'll see that the sockets on the left-hand side of the TinySA are labeled low and high. And this referred to frequency ranges. The low frequency range is almost DC to 350 megahertz, which will cover most of your needs, unless you're going to 70 centimeters and beyond. The upper one labeled high is 240 to 960 megahertz, with some limitations. And I'll say more about that in a minute. The thing that I particularly liked about the the TinySA as soon as it arrived was because of the similarity in look and feel. Within 5 minutes of taking it out of the box, given that the battery was already partially charged, I was able to do this, which was to attach the internal antenna, set up an appropriate frequency range on the display, and take an immediate snapshot of the VHF FM broadcast band in my locality. And so those are the positions and frequencies of the FM broadcast stations in the London area. And it was that simple. It was that straightforward. Now, I could have refined that display in a number of ways, whatever, but it was so easy to do. No difficulty there at all. And I say that's just with the little internal antenna that's attached to it there. So that was without reading any of the documentation. Just jump in and try it, and it worked. Right, a bit about the documentation itself. Unlike the Nano VNA, where again the documentation is kind of scattered across the internet, shall we say politely, and there have been attempts to gather it together, whatever. The documentation for the TinySA is extremely good. Start at their website, TinySA.org. Loads of information there straight away. Full specifications of the device. The hardware, the design is protected. That doesn't mean it's not available. You can find out all about it. It's protected simply sort of as a copyright. The firmware design is effectively public domain. They invite people, they give you can get full details of the firmware. And if you have the skills, you can modify it yourself. And if you think you've come up with a good modification, let them know and they'll consider incorporating it. In fact, there's been a couple of updates since I acquired mine. I haven't dared try them yet, but I'm sure there'll be. I thought I'd get this talk out the way before I tempted fate by changing the firmware. There is a 35-page manual which you can access through the homepage of TinySA.org. Again, written originally in Danish, but translated into a very good version of English, which is almost the same as the language you speak. And it's called the Description of TinySA, a Real Spectrum Analyzer for Little Money. Rather long-winded title. 35 pages. Luckily, I mean, I went to school. When I went to school, I was never taught how to swipe a screen. I was taught how to turn over pieces of paper. And so I still prefer to do that, particularly with an initial introduction to something. And so I like paper. Now, luckily, I have a color laser printer that prints both sides of the paper. So this was only, 18 sheets of paper to do this, but it is worthwhile. I mean, this will tell you all you need to get started on it without a doubt. But on top of that, Eric Kasuk has his own YouTube channel there, and he has 26 short videos on the channel about doing specific measurements and the best way to do specific measurements with the TinySA. And by short, I mean they range from just over 3 minutes to about 20 minutes. Most of them are 5 to 10 minutes, no more than that. And they simply concentrate on what you need to know. So definitely recommended. There are, of course, other YouTube users who have posted videos on the TinySA. Your mileage may vary. There's one or two I've learnt to avoid. It would be wrong of me to name any names on here, but be careful, because there are some people on YouTube, believe it or not, who know little or nothing about what they're talking about. Okay, here's a block diagram of the main structure of it, which I'll just go through briefly. Now, some of you may have noticed on the earlier pictures that the sockets, the low and high sockets, are marked as inputs and outputs. That's because, depending on how you set things up, they can be used for either purpose. It can be used as a rather sophisticated, in some respects, signal generator as well, which can help you to make measurements. So let me concentrate first of all on the low frequency channel. This is the one that goes up to 350 megahertz. The first stage is an attenuator, and the attenuator can be manually controlled, or it can be controlled from the microcontroller unit, the MCU there, with the idea in mind of automatic gain control to try and stop you blowing it up with too big a signal coming into it. And it will do its best to protect itself, like all good robots. No guarantees though. Don't connect it directly to the RF output of your IC 7300 and pump 100 watts into it. It will not like it, but you wouldn't do that anyway. So there is this attenuator as a first stage. Also, as I'll mention later on, the attenuation is quite important to get to condition the input signal into a range which reduces, as far as possible, the presence of artifacts and spurs. It then goes into a low pass filter according to the frequency range or the measurements that you're doing. And the purpose of the low pass filter is to cut out, mainly is to cut out any noise at higher frequencies that you're not interested in. Okay, so it's kind of a noise reduction thing there. It then goes into a mixer, where in fact I believe it's shifted down to audio frequencies for further processing. And then there's the bandpass filter, which again selects out sections of the frequency range that you've specified and samples those in time in order to do the necessary processing. And there's a switching system there that switches between these blocks that are marked as receive and transmit. Now the receive, of course, is measuring the signal amplitude for the microprocessor to deal with and then display. The transmit is effectively a signal generator. And I say the signal generator does have certain other features like amplitude modulation, frequency modulation for particular testing purposes. And these signals can be fed back through that chain of devices, and the low output input can be configured as an output. Going over to the high frequency, this extends the frequency range up to nearly a gigahertz. But, warning, the designer makes it absolutely clear that as far as he's concerned, this is a free bonus part of the circuit. Okay, there are limitations in doing this. Without any doubt, there are limitations in how it handles this. And there's certain things you cannot do at the higher frequencies or don't have the same resolution or accuracy or so on. But, you know, this is something you have to decide whether it's good enough for your purposes or not. So this only has the switching system in it, together with the use of the mixer from the low circuit, receive and transmit again as a signal generator output from the high socket, and again connection through the microcontroller to the display. The one other thing that you'll see on the block diagram there towards the left is a calibration generator. And this is quite impressive, really. This is a small 30 megahertz temperature controlled oscillator at a very precise, I think it's minus 25 decibels, but it's a very precise level. And this is used to calibrate the frequency ranges initially. Now, because of the way this is organized, obviously the way this works is you connect the high output with the calibration generator through to the low input. You could in fact connect they make it clear you could in fact connect a better calibration standard in order to carry out the calibration. So if you've got a GPS regulated system, a rubidium clock in the corner of your workshop or not, and believe me, I know radio amateurs who have, you could make use of that. Now, personally, I think the calibration generator in the TinySA is perfectly matched to the capabilities of the TinySA. You know, there are limitations in its resolution and so on, and I don't think having a significantly better calibration generator is going to necessarily give you more accuracy. So I think the internal one is good enough for the purpose of operating this device, but it provides an option there. That's the important thing. Now, calibration, those of you who know the nano VNA, you know that calibration is everything. You have to go through calibration process on the nano VNA with short circuit, open circuit, 50 ohm load, channel 0 to channel 1 transmission. If you're using both channels on the nano VNA, you have to do it for the frequency range that you choose. Ideally, for good results, you have to determine whether you want to include the cabling or set up a measurement plane somewhere else. The nano VNA and VNAs generally are all about calibration. This device isn't. Okay, calibration on this is dead simple. You run one calibration test whenever you feel like it to check the frequency, the accuracy of the frequency display. It then runs through a series of 8 self-tests internally, and if they all come out green light, you're ready to go. That's all you have to do. Operating this device is not about regular calibration. It is all about watching out and avoiding those artifacts and spurious signals. So that's something I want to emphasize there. There's a lot of discussion in the documentation about dynamic range, and this is absolutely vital to your use of any spectrum analyzer. At the bottom end of the dynamic range, there's the noise level. Like any electronic device, the TinySA generates its own noise. It's remarkably low by the use of modern electronics, without a doubt. It's remarkably low, but if you want to measure noise, you might be trying to measure something of a similar noise level in maybe a device that you've built, an amplifier circuit or a mixer or something like that. And at least the documentation, including YouTube documentation, explains how to go about checking whether the noise that you're measuring comes from the TinySA itself or from the device you're measuring. Okay, that's the important thing. And to some extent, to account for the internal noise of the device in order to make quite sensitive noise measurements of equipment outside. Then there's the OK region of the dynamic range. Everything should be all right there. Then you've got what's called the distortion region. And this is where you're getting to a significantly high input level as far as the circuitry is concerned, and you risk starting to generate these artifacts and spuriae from distortion in the circuitry. The final level, of course, is the danger level, and there are a number of different levels of danger. The lowest level of danger is you are definitely generating artifacts in what is displayed on the screen. The TinySA will do its best to avoid this, but at the end of the day, if you instruct it to do things a particular way, it will do it that way. And you risk getting results that are not very meaningful. Then there's the other end of the danger range, which is you let the magic smoke out. Okay, and again, it will try to protect itself, but obviously there are limits to that. Most of the YouTube videos, or a significant number of the YouTube videos that Eric Kusshoek has on his YouTube channel, are about making the OK region as wide as possible in terms of signal intensity. Okay, keeping the noise as low as possible and the distortion and danger region as high as possible to get the best possible, most meaningful results from the device. Okay, so here's some examples now of doing this. This is some amateur on the 2 meter band who just happens to be transmitting on the frequency that the Eccleford Club uses for its Sunday night 2 meter net. You see he's got a nice new transmitter. He is apparently transmitting on a reasonably accurate 145.325 megahertz frequency, which is the one that we tend to use. There's a signal strength indicated there. Oh dear, look at the bottom of that plot. Notice that the text at the bottom says that this starts at 144 megahertz, ends at 146 megahertz. That's the limits of our 2 meter band over here. And each of those vertical gradations on the x-axis, if you like, are 200 kilohertz wide. You can see that this person's transmitter has a skirt on the bottom of it that is 300 kilohertz wide. This guy is taking up most of the band. How outrageous. Well, actually, of course, if you haven't guessed, this guy is me. The signal is coming, is a 5-watt signal from my Yaesu FT991A, going through a collinear antenna at 5 watts, about 30 meters away from where I'm sitting now and where I was doing this measurement. I've put the telescopic antenna back on it and I'm monitoring my own signal there. And oh, I'm so embarrassed. Look at that. It's awful. On the other hand, did Yaesu really sell me a radio that was that bad? I can imagine lots of you sitting out there going, yes, they probably did. But we'll leave partisanship of radio ownership out of this. I somehow think it's unlikely. I somehow think this is maybe an artifact. So next experiment, engage the internal attenuator. If you look on the left-hand side of the screen, you now see that the word atten is in green, which means the attenuator has been engaged and it's attenuating the input signal by 25 dB. And this has pretty much cured the problem. Okay, that skirt that you saw before, the 300 kilohertz skirt, it's not real. It's an artifact generated because the signal input was just too high. Now, if I'm only measuring the frequency, it doesn't matter. That measurement would have been fine, didn't have to do anything. But actually the signal is not as bad as it first looked. And that's sort of first introduction to artifacts and problems that could be generated. This is what you've got to be aware of when you use this device. Okay. There are limitations to the bandwidth there. RBW, receive bandwidth, again, it says on the left-hand side of the screen there, 14 kilohertz. So that's the actual resolution bandwidth of each point is 14 kilohertz. Obviously quite a lot, but I could narrow it down. It's because I'm looking at the entire band there. Incidentally, it also points out there's a scan time there of just over half a second. The scan time can vary quite a lot. It can be several or tens of minutes, depending on how you set it up. But there are lots of ways to change the bandwidth, change the range that you're looking at, change the overall, the way even that it acquires and processes the signal to speed that up. If you want, depending on whether you want a rapid display or whether you want a very, very accurate measurement over admittedly quite a long period of time. So again, all these adjustments were there. So the point I'm making there, if I haven't already made it clearly enough, the TinySA relies on the user identifying and avoiding situations where there are artifacts and spuriae on the screen, as do most spectrum analyzers, if the truth be told. Ah, yes, the naked truth. This is the picture that's titled "We did this so that you don't have to." Actually, better than that, a friend of mine did this so I didn't have to. But actually, excuse me, opening up the TinySA is not a big deal. It's not full of hundreds of tiny springs that fly out all over the room as you take the last screw out and distribute themselves all over the shack carpet. It's actually very user-friendly for opening up in this way. And the nice thing you can see about it is that all the RF circuitry is nicely shielded. If you have a tiny nano VNA, do the same thing on that, because, please excuse me, because if you've got a nasty cheap clone, some of that or all of that RF shielding may not be there. You have been warned. But the TinySA is properly manufactured. There are good quality assurance measures in operation there. And this is what you should see. It's nicely made. The processing, you can see the central processor there. That is shielded from the RF circuitry coming in, and vice versa, of course. There will be clock signals outside, off board there that you don't want coming into the input. Okay, applications then of what you can, some applications, and what I've done here. I mean, I'm going to go through these quite quickly because I am mindful of the time. Most of these are from the TinySA documentations. Some are items that I put in myself as being, I think, particularly relevant to radio amateurs. The first one is measuring harmonics in a transmitter output or a signal generator output, whatever. Very good at measuring harmonics. Again, I'll show you a bit more to do with this later on. Measuring spectral purity, which can be associated with harmonics, but also looking for breakthrough of digital clocks. Again, other signals that shouldn't be there. in the output of some kind of oscillator or transmitter or amplifier. Measuring phase noise, again, quite important, particularly in a lot of modern RF electronics. There's a lot of concern about keeping phase noise to a minimum. Again, it generates phase noise of its own, but there are ways of making comparisons and taking this into account. So you can do quite good measurements, quite accurate measurements of phase noise with this device. Measuring third order intermodulation. If you don't know what that means, don't worry about it. But if you read the usual ARRL journals where they do their own lab tests of transmitters and other products and compare them with what the manufacturers claim, you'll come across third order intermodulation measurements. So it is considered to be an important criterion in the performance of modern transmitters, without a doubt. Measuring IQ balance, that's nothing to do with intelligence quotient, it's to do with quadrature detection, which is relevant to some software-defined radio systems. You can do those kind of measurements. Measuring dynamic range. Dynamic range, of course, is vitally important in all aspects of radio. If you consider a signal coming into your antenna at microvolts, having to be finally resolved through headphones or a loudspeaker at something you can hear, the standard design criterion is something like 100 decibels of amplification between the antenna and you actually hearing the output. And again, for those of you who are not particularly familiar with decibels, 100 decibels is 10 to the power of 10. Okay, so that's 10 billion times multiplication. That's why these things are generally displayed in decibels. It's huge. It's an enormous range of signal intensity, and both the measurement of it and the display of wide dynamic range signals is absolutely crucial to all aspects of radio. Measuring low frequencies. Now, as I say, the display claims to go down to DC. In fact, what you see if you go right down the low frequency range on the TinySA is you see effectively an increase in noise and a total lack of linearity. It's not, they make no claims whatsoever for its response below 10 kilohertz. And there are certain guidelines to apply if you're looking at less than 100 kilohertz. So maybe testing your Alexanderson alternator system might be a little bit iffy, but most of us are operating well above those kind of frequencies. But it can do quite good performance at low frequencies. Identifying well, electromagnetic interference, or maybe call it RF interference sources. Yeah, stick the aerial on it, take it around the house. And I'm sure you've done this with a transistor radio of some kind. You may find that unless it's a good shortwave transistor radio, you know, certain frequencies are excluded. But you can take it around the house and look for anything from nearly DC to 960 megahertz for interference sources. I did this. I found what I already knew, that the only major source of interference in my home is two small fluorescent lights under a cupboard in the kitchen. Now, the interesting thing about this is I've only ever had a problem from them because we have a flat roof over our kitchen where I set up experimental aerials. And the only problem I've had is when I'm using my 6-meter homebrew Yagi on that flat roof. I can definitely hear the noise when those lights are on. So I come up to the shack on the top floor, and then I have to text my wife to ask her to turn the light off. I was able to identify that amazingly, these fluorescent lights only produce RF noise in the range of 45 to 60 megahertz, almost designed to clobber the 6-meter band, but nowhere else. But it just confirmed what I knew, but gave me more information about it, you know, and that's, you know, that kind of information can be very helpful. My my smart power meter and my solar panel system, which includes a Tesla battery to store electricity, no interference at all. Can't measure anything from those. They are well made, and I made sure they were well made when I bought them and had them installed. But it's a nice check to make sure that I'm not getting problems from those. Tuning sweep settings. If you're scanning or if you're sweeping frequency, you can set up the TinySA as a signal generator sweeping frequency. You can also incidentally sweep amplitude on a single frequency signal to test the linearity of for example, a linear amplifier. Very useful there. The impact or effect of coax cable, for example, the effect of feed line, whether it be just simply a case of your feed line losses, you can measure, or indeed that there's a fault somewhere in the coax cable which is causing distortion, measurable. You can measure FM deviation, you can measure AM modulation. There are specific menu items to help you do all this. Measuring 1 dB compression point if you have a compressor system. A pan adapter display for your receiver. I thought I ought to demonstrate this. My receiver in my shack just in front of me here actually is a nice old Icom R71. I love it. It's a nice old receiver. It's got proper knobs and switches. I don't need a computer to operate it, but it doesn't have a pan adapter display. And in fact, I don't think Icom ever made a pan adapter display for it, but it does have an output labeled scope on the back. And this, of course, is the output from the first intermediate frequency stage before any filtering occurs. And it's from the first mixer, effectively, at about 70 megahertz. So there you are. You can set up. I mean, I've done it before actually with one of those little SDR dongles on it, but that takes up a whole laptop of display. And you can use the device here. As you see, it has a waterfall display as well that you can set up. Very quick and easy to set up. And that was the part of the 20-meter band this afternoon here in Britain. And a nice display it provides too. And this is where the cost of the TinySA is a game changer, okay? Stop thinking about in terms of, do I really want to tie up my spectrum analyzer as a mere pan adapter display for a radio that's too old to have one? Start thinking in terms of, hey, for 60 bucks, I could put a pan adapter display on my receiver. Okay, and I think you've got to start thinking in those terms. There is a tendency for people to say, oh, you know, I know people have got the nano VNA and they only use it for SWR measurement. Or I know somebody who's got a TinySA and he only uses it as a pan adapter. But hey, it's only 60 bucks. You know, if you have a single use for it at that kind of money, is that a big deal? Personally, I have other uses for it, but when I get a bigger screen one, it may well find a permanent home on top of the R71 there. It works extremely well. So that's an example of that. Going back to the list, you can set it up with a tracking generator to measure a mixer performance. Again, if you don't know what that means, don't worry about it. You could measure the noise factor of an external amplifier that you've built for yourself. These are some of the things that you might find useful, and I think that's a pretty comprehensive list down there. Okay, some other examples here, keeping an eye, as I say, on the time. Transmitter power output. In the first COVID lockdown of 2020, I built this little QRP power meter. For various reasons, I wanted it to go up to 20 watts. Sorry, QRP over here is 5 watts. I know it's anything less than 1.5 kilowatts with you, but it's 5 watts here. And also, I also built what you can just see to the right of it there, the quarter pounder, a 250 milliwatt output top band AM transceiver. One transistor, okay, count them, one. I have no use whatever for this device on a day-to-day basis, but when you're faced with a circuit that says with one transistor and a crystal, you can build a top band AM rig, you've got to try it. I mean, I've got to try it anyway. So I did, and it worked, and I have QSOs to prove it. It said you can expect about a quarter of a watt output from it. So I put it on this RF power meter. Okay, it's a nonlinear scale, even with the expansion of the square root law scale at the low end. Okay, it's saying between 0 and half a watt. Okay, that's fair enough. That's fair enough. But of course, I want to know it slightly more accurately, and now I can. So here's the same device with its carbon microphone, going through a little switched attenuator. I could have used the internal attenuator in the TinySA, but I wanted to be ultra protective of my new toy. So I fitted it with the external one as well, and connected it up and gave it a try. And you can't quite see the display very clearly there, but here it is in close-up. It was transmitting on 1.992 megahertz, which is the crystal frequency. And I've changed the display scale to a linear scale in milliwatts. And I've also, if you look down at the left-hand side, it says amp minus 30 dB. So I've told it there's an external amplifier stroke attenuator in this case, applying a 30 dB attenuation to the signal, and it corrects the display on the screen to take that into account, and it tells me the output is 268 milliwatts, which I think is pretty good. You know, that I'm happy with that. It does vary a little depending on how loud I've just shouted into the carbon microphone, and or how hard I put the carbon microphone down on the desk, because because of course the carbon microphone, if you haven't already guessed, is just in the emitter circuit of the one transistor oscillator that this uses. But it works, and there's a result. To me, a useful measurement. I can put it on a logarithmic plot. You see on the linear plot, you don't see the noise at the bottom of the display because it's too small to measure. This is why you use a logarithmic plot to expand the low signal there. And you can just see a bit of a hint of AM modulation and some sidebands appearing in that particular display there. You'll also see that the frequency measurement has changed slightly. If you look at the top there, you can see that the marker, that's an automatic marker, by the way, has moved slightly over to one side, the low frequency side. And in fact, the resolution bandwidth is only 3 kilohertz anyway. But it gives you an idea of how this is, how this transmitter was performing. And I also wanted to know about the harmonic content. Now, it contains, the transmitter has a small low pass filter in it. Probably for higher, certainly for higher powers, it wouldn't be considered adequate. So I expanded the scale on this up to 10 megahertz to look for harmonics, and there they are. And you can look at this in two different ways, really. Now, of course, It was only after I'd taken this photograph and done this measurement that I discovered that the TinySA has a harmonic measurement facility built into the menu system. I hadn't got that far in the manual yet. I just have to try things out, you know. And in fact, what that does is it would identify the first 4 peaks in the series and give the signal level and frequency of each of those 4 peaks, just to confirm that they are in fact true harmonics. In fact, this one worked out quite well because, again, I haven't particularly set the reference level for the measurement, but you can see that the second harmonic there is at virtually 0 dB on the scale, and the fundamental is at nearly 23 dB microwatts higher than that. So again, a quick conversion in the head, 23 dBs is about a factor of 200. So in fact, what you're looking at there is a difference in power by a factor of 200 between the fundamental and the first, the second harmonic, the first overtone, if you like. So that, that second harmonic is at about 1.2 milliwatts. Now, 23 dB down is not very good by modern standards, but this is a 1 transistor, you know, trick pony. On the other hand, 1.2 milliwatts, out of band, admittedly, it's around about 4 megahertz. Is anybody going to hear that? Well, not at the noise levels around here, I can assure you. I can't even hear it on my own receiver. In the shack. I've looked for those harmonics and I can't hear them, but to be honest, that's good enough for me. So I can do this harmonic analysis and I can see they're there. I think, I'm sure all, or most of you will know about WSPR, Weak Signal Propagation Reporter. Again, if you don't, the scheme is you send out a signal, low power, through your antenna. It's picked up at possibility of stations all over the world. And when they receive your signal and identify it from your call sign and location, they send the information back to a central database on the internet, which you can look up and you can see where your signal is being received at a particular time of day or whatever. It's great. It's the way of checking, of really checking the performance of an aerial system, as well as what propagation is happening, you know, what propagation is like at the time. So, so I'm a big fan of WSPR. And in the UK, we have a company called SOTA Beams, which I think you may be aware of in the States. And they came out with this fabulous device some years ago called the WSPR Lite. The WSPR Lite is a package 2 inches by 2 inches by about ½ inch thick. And it you connect it with a USB cable to a computer. You program it with your call sign, location, and standard WSPR information, including the power output. And then apart from providing power to it, you set it running at exactly 2 seconds past an even minute, and WSPR stations, hopefully receivers, will find you and report back all around the world. It's a wonderful little device. It's not particularly expensive, and once it's running, it's totally self-contained. You don't have to do anything else about it. So naturally, I had to have a look at the output of it just to see, and there's a picture of the output from this this clever little device. There's a close-up of it. This is using frequency shift keying to encode the digital information, and so you can see some of the performance criteria there on the 2 meter WSPR frequency range, which is just a tad below 14.1 megahertz. Now, a very good friend of mine, Skip, N2FOE, who I've known for nearly 20 years, came to visit in the UK, came to visit me in the UK about 3 years ago with his wife. And I showed him the Whisper Light and he said, I've got to have one. This is a gadget I have to have. So he actually purchased one with his credit card while he was here in England. And it arrived 2 days later. So he took delivery of it and took it back to the States with him. And I said to him, do bear in mind that the Whisper Light, though low power, has no harmonic filters in it. You will need to provide a low pass filter, harmonic filter for the output. And he said, well, I've got some in the shack at home. I've got components to build other ones. So that's not a big deal. 2 weeks after he returned to America, he emailed me and he said, Phil, I'm absolutely desperate to try. I just got around to sorting things out since I got back. I'm absolutely desperate to try out this Whisper Light device. Do I really need a harmonic filter on it? And I said, if you really want to be legal, yes. What I could have done now, of course, is I could have said nothing but just sent him this picture. Does the Whisper Light Flexi really need a low pass harmonic filter? Heck yes. It's a digitally derived radio signal. It's practically a square wave that comes out of it. And I think this plot makes it absolutely clear, yes, the Whisper Light Flexi really does need a low pass harmonic filter. Simple as that. And of course, to go a stage further, I have a set of filters for mine, of course. I could have put those on and demonstrated, well, I have demonstrated to myself the effect of using such a filter on the device and how effective it is in reducing these harmonics. So that's the example of some of the measurements. Now the summary. Do I need a TinySA? By which I mean, do you need a TinySA? If you haven't understood a word of this presentation, no, you don't need it. You're not ready for it yet. You will one day, but you know, you don't at the moment. If you have to have all the latest gadgets, then obviously the answer is yes, because it is the latest gadget, without a doubt. And then, yes, on that basis, you need to have one. And I know several people in our club who have one. They have no idea how to use it, but they will one day. Now they've got it, you see, they can start to learn. What if you already own, this is a wild guess at price, a $1,500 portable Rigol spectrum analyzer? No. Actually, all the Rigols I've seen over here have can be quite portable, but they're all mains connected ones because the Rigol uses quite a lot of power. I presume there are lithium battery powered versions now. Maybe one of you has one or something and can tell me this. But if you have a portable spectrum analyzer of that kind of quality, then again, the answer is probably no. You don't need this. On the other hand, if the pride and joy of your shack, workshop, laboratory, whatever you call it, is a 40-year-old Hewlett-Packard or Roder and Schwartz device that you rescued off a skip from your former employer with a serious screen burn on the CRT, you nearly gave yourself a hernia getting it out of the boot of the car, a trunk of the car, and onto a shelf in there, and you really don't want to risk the injury that you would cause it or to you by moving it now, then yes, you need a TinySA. It's all very well taking equipment to your test gear, but there are just some times when it's easier to take the test gear to what you need to test. And I'm not decrying your 40-year-old Hewlett-Packard or Roder and Schwartz spectrum analyzer. They're great machines, but portable, many of them are not. Right. If $60 doesn't leave a serious dent in your finances, and let's face it, you spent 2 grand, 5 grand, or in Neil's case, at least 10 grand on your transceiver, and you have far too many of them anyway, yeah, you probably could find use for a tiny spectrum analyzer in your toolkit. I mean, it's $60 and it fits in your shirt pocket, literally fits in your shirt pocket with its antenna. You can take it to your, I think you were talking about having lunch meetings as we do here. You can take it along there and show it to your friends and say, look, these are the local VHF FM stations. Impress your friends for only $60. You need to, of course, you'll all turn up with them and nobody will be impressed, but at least you can compare notes on it. And if you have a nano VNA and it's showing signs of loneliness, then yeah, buy its younger brother for company, because they do look so nice together. And in fact, there is a video on Eric Kashuk's YouTube channel, which is called the TinySA and the Nano VNA testing each other simultaneously. And I think that gives a lovely idea of what you can achieve with them. Okay, I've gone on for longer than I should have done, I'm sure. Thank you very much for your attention. Thank you for inviting me along this evening. And if you have any questions, I will do my best to try and answer them as best I can. Thank you. Now, how do I get out of this or get it so I can hear other people?
So, so the first thing I think you want to do is stop sharing.
Yeah.
And then I think everybody can unmute themselves or use their space bar to talk and leave themselves muted. It's up to them.
Right.
Let me.
I have to. I think I have to pass control to somebody else. Is that you, Mike?
You can either pass it to me or you could just say stop sharing.
Okay, I've stopped screen sharing now. Yeah. Okay.
And you're all done.
Okay.
Let me make an observation, Mike, and I think you're aware of this, that in reading the manual that Phil mentioned, Eric indicates that there are a number of counterfeit TinySAs, and he tells you how to check whether you have a real one or a knockoff. And I know for a fact that in England, they pay about 60 quid for the TinySA, and it's about $50 plus shipping from R&L. R&L in Hamilton, Ohio is listed on their website as the official US distributor for the TinySA. So if you're going to get one, don't go looking for an El Cheapo on Amazon, because you're liable to get garbage. And don't be penny wise, pound foolish, as the saying goes. R&L is wonderful to work with. I ordered one. I had it in 2 days, and it came in today, as a matter of fact.
Well, that's great, Neil, and I will echo that. R&L did a fine job of sending me the one that I purchased, and I still haven't had an opportunity to play with it yet, but I do like the box that it came in.
Yeah, it's a nice gift box.
Yeah.
Well, I need to say thank you very much, Phil, for the wonderful presentation that you gave us. It was deep enough technically to keep you interested, and interesting enough from the non-technical standpoint to show you what you can do with it. So I really appreciate that. Thank you.
Thank you.
And thank you for staying up so late.
Oh, that's fine. So I'm just getting into my stride now.
Well, okay, we've got any questions that we want to ask Phil?
I've got a question.
Yeah, go
Sure.
ahead.
If your rig doesn't have a scope jack on the back of it, can you connect the TinySA as a pan adapter to it, like my K2 as an example?
If you're prepared to tinker about inside, then I would say yes. All you've got to do is to get the output from the first mixer stage before it goes into the IF filters, and buffer and condition that to a suitable signal level. It may be perfectly adequate, or it might need a little bit of amplification. But yes, and the as far as is possible for most of the range, the input impedance of the TinySA is maintained at 50 ohms. So it varies a little bit outside the ranges, but of course, now one thing you have to bear in mind is that it will put on a display centered around the IF frequency. It won't actually display the actual frequency, but presumably your receiver's got that anyway. It's just nice as you scan through, you can see the peaks either side of your present position and select them. So yeah.
Right, very useful. Thank you.
Pleasure.
How about anybody else?
I just wanted to say thank you, Phil. That was a great presentation.
Thank you very much. Obliged, most obliged. And thank you for inviting me. I've been looking through the lists. Thank you, Lisa. I've been looking through the lists of your previous speakers, and I'm honoured to be in such good company, and with all of you as well. Thank you, Tyler.
And I had a comment too, Phil.
Sure.
It's really great to hear proper English spoken.
Oh, well, Neil knows, you see, that I'll come from Southeast Essex, and normally I would talk like this. But, you know, having moved to Surrey, which is a posh part of England, one has to speak the Queen's English, and particularly that, keeping it clear, I think, is the main thing. I see. Yeah, I was just seeing Diane's comment there about a draw for a free TinySA. Yeah, that's all right. I don't have to take the blame for that. That is entirely up to the generosity of your committee.
Well, we will investigate whether or not we can work something out with R&L Electronics on bulk purchases. So we'll be back to you on that one.
You know, hey, Wes, you're talking about Phil speaking proper English. Philip knows that my old friend, Tom Southwell, G4FEU, was a Geordie, and the Geordies are from way up north. And the first time Tom lapsed into that Geordie dialect, I looked at him and I said, I didn't know you spoke Serbo-Croatian.
We lad. Yeah, I went to university. I told you I went to university just south of Newcastle on Tyne, which is Geordie land. And the truth is there are so many dialects around there in quite a small area. You know, if you look on the map, Newcastle is right next to Gateshead. It's just north of Durham, which in turn is just north of Darlington, and they all have different dialects that they speak. But yeah, some are very broad indeed.
Thank you, Phil. We really appreciate your presentation. And Mike, did you look over all the chats to make sure that we've covered anything that someone may have asked Phil through the chat area?
I'm scanning through them right now. I don't see anything. I think we've got everything so far. So
I had looked through, and there's been some very kind comments for which I'm grateful. I don't think I've missed any particular questions there.
Hey, Phil, real quickly on the when you're connecting up signals to it, I mean, I'm assuming it's all 50 ohms. You want to keep everything terminated at that level, or?
It does say in the documentation that the intention has been to keep everything at 50 ohms. But they do admit to, at the extremes of frequency, they do admit to the fact that it can vary away from that. They're not very specific as to how far. You could, of course, always put a further attenuator stage in to give a better input presentation of 50 ohms if you needed to. And quite often you need an attenuator anyway, so that wouldn't be too big a deal. But they don't guarantee, they don't go to the extremes that some other manufacturers go to, again, because of keeping the cost down to a reasonable level. But they attempt to as close as possible to 50 ohms.
And now that you've had yours just for, I mean, you've been playing with it and you found, so buying the unit itself, obviously, have you found that there was some other things that you maybe would have purchased along with it the first time to kind of round out your purchase to make it more effective, like short stub cables or whatever? I mean,
not really, no. Well, only because, I mean, you know, I've been collecting test equipment and cables and things like that for a good many years, so I have most of those things to hand anyway. No, the short cables that come with it are very useful. Occasionally, you might want a slightly longer one. I used a longer interface cables and an adapter to do the pan adapter demonstration. Just to put it in a more convenient position. Apart from that, no, not really. And well, as I say, I don't like the guitar pick touchscreen activator very much. Again, it's cheap and easy.
yeah.
But I mean, you know, who doesn't have a desk drawer full of leftover styluses from all those old touchscreen devices that you threw away years ago? And you know, so.
Yeah.
You could use your times 10 probe off of your scope if you have it right to
well, yes, that
poking around and not loading down the circuit. I mean, it seems like that would be an obvious thing.
Yes, yeah, good idea. Yes, I mean the other thing as well is say as regards the touchscreen, I don't have fingers that work on touchscreens. Whether my skin's dry or whatever, I have a serious problem with touchscreens. They don't respond to me at all. So again, I do need a stylus or whatever to do that. But no, I think the what's in the box is very complete, you know, to get you to the point where you can start doing serious measurements.
Thank you.
So Phil, we have one last question, I think, that came in. Kevin, W4KOS, has got a question. He's been watching Foyle's War on DVD, and he wants to know if that was a big show in the UK.
Yes, it was. I have to confess, I haven't watched it, but yes, it's because you can't watch everything. Yes, I know that it is a very good series by reputation, and yes, it was very big over here.
Hey,
And
it's
we've got
about
a couple other little quick questions, and then I think we can let you go. Dwayne, KB4QB, has a question. Have you tried it with a tracking generator?
Not yet.
Okay.
But I will be doing so, yes.
All righty. Well, again, thank you very much, Phil. It was very informative. Glad you were able to join us. Come back anytime.
Thank you very much.
And
Bill, is there anything that you would like to ask anyone here in the U.S. On any other particular subject that might be of your interest?
Well, I have a significant, I'm very pleased to say I have a significant number of friends across the USA. I've always found Americans very, very hospitable. It's probably just the accent that does it, of course, but I'm well in touch, and I'm glad to have made another possibly 63 friends or 62 friends this evening. Thank you just very much for supporting this talk. I've never been on Zoom before with more than one screen full of people. So that was quite a surprise. I've learned a bit about that myself. Thank you for the support you've shown for the talk. I'm glad those who've said they enjoyed it have enjoyed it, I hope. And I'm grateful to you I'm honored to be invited. Thank you.
You had actually 77.
Wow.
Oh,
that's definitely a record. We're not going to do that at Eccleford because we only got 50 members.
well, you could invite some of us. We might be able to, get up early.
Oh, yes, yeah. I mean, I think when we discussed the possibility of a joint meeting, didn't we? At some point, a link up between the two clubs, perhaps. But yeah, it's great. I mean, I think I made the comment before that, and certainly Neil knows that we kind of reluctantly, as a club, dragged ourselves kicking and screaming into the 21st century with Zoom when we could no longer have face-to-face meetings during the lockdown. And it's proved so successful in so many ways, not only being able to have Neil join us on a bi-monthly basis. We also have a long-term member who now lives in Northern Ireland, who's been able to join us. We have elderly members who don't like going out late, or certainly don't like going out in the winter. The result of which is that that we are now, the committee's already decided that even when we are able to resume full meetings, we will have regular Zoom meetings as well, because it attracts a different subset of our membership. So it's a very effective way of doing things.
Yeah,
Right now, they meet twice a month. And for us, it's a bonus because it's about 2:45 to 3 o'clock in the afternoon. So we get the benefit of that. And the meetings are good. There are a few of the fellows in there. Phil's really easy to understand. But if you get a Scot, they can be a little bit dicey trying to understand the Queen's English, or what it's supposed to be.
Well, the Queen's Scottish, yes.
There is a difference. Well, okay. Thank you again.
Thank you.
Thank
We've got 9:15 here, so
Thank
I'll
you.
let you go.
All right, thank you.
Thank you.
I'm already in my pajamas, you see, of course, for the whole talk.